All right, so let's talk about acceleration. So we've talked about acceleration before, about speeding things up and slowing things down in a line. We've also talked a little bit about acceleration as a vector. But what I'd like to talk about now is what happens with acceleration. Acceleration can be broken down into your x and y components, like we talked about previously. But acceleration can also be broken down into two components, one that describes turning, the change in the velocity that describes how the direction of your motion is changing, as well as one that describes speeding up and slowing down, irregardless of whether or not you're moving in a straight line or not. So we'd like to break this down into two parts, right? One is going to be the turning part of the acceleration, often called centripetal acceleration because it's pointing towards the center, and the other one called the tangential acceleration. So we're going to start with the turning acceleration, and basically what we're going to say is that when an object moves in a circle, at a constant speed, then the acceleration points towards the center of the circle. Okay, so let's try to draw that. First, I'm going to try to draw on this a circle, which is pretty iffy. Okay, and that's going to have a center here, there, and then we'll have a radius. Let's go over just to this spot here and say that our object is moving with a speed v here. All I've said so far is that the acceleration for this object is pointing towards the center of the circle. So that's the acceleration, and we'll call that the turning acceleration AR because it's going along the radius of this circle. You can also call it the centripetal acceleration. Okay, so we've got this circle. The acceleration is pointing towards the center because we're moving at a constant speed along the circle. So we're always turning, and we're always moving at a constant speed along the circle, and wherever we are, that acceleration points towards the center of the circle. Okay, so we can also calculate, we know how to figure out what that acceleration is. So the radial acceleration is one proportional to the square of the speed and inversely proportional to the radius of the circle. Right? So we can just write that as, say, AR is equal to V squared over R. So that's all we need. So the faster you're going, the more acceleration you need. That makes a little bit of sense, because what's happening here is you're starting here, right? This is where you're going there, and then you're coming over here like that, and you're going from this V to that V, right? So if you were going in a straight line here, let's just flip this over. So if I was going in a straight line here, I would, when I got to this radius, be way out here. So I need an acceleration pointing this direction so that my speed now is going in this direction, so I stay on that radius, right? So, right, I'm here. I come out here. If I'm going in a straight line, perpendicular to this circle, I come out here. So I have to pull in directly towards the center. I need some delta V this way in order to be moving perpendicular over here and to stay on the circle. Whenever I'm moving along the circle, always perpendicular to the circle, right? So that's going to keep us along there. That's what we're doing. So the faster we're going, obviously, then the more of that acceleration we need. And the larger our circle, the less of that we need, because we end up being closer, right? If this was a larger circle, the direction here would be less steep over that, and this would be closer. So we'd end up, over the same amount of time, needing less acceleration. Okay, so that's our turning acceleration. Next, we'll go into an example. After the example, we'll hit our tangential acceleration that will speed us up and slow you down, and then we'll talk about the vector parts.